The 11th question, it says that consider the following statements related to the pore pressure parameters A and B given by Skempton. Does A lie between 0 and 1? No. A can be less than 1 and A can be greater than 1 depending upon the type of soil. A can be less than 0 or greater than 1, that is right. B always lies between 0 and 1, that is also right. B can be less than 0 or greater than 1, that is wrong. Therefore, only two statements are correct, that is Q and R. Now let's see the concept behind it. The concept is that, if it is not possible to measure the, pore pressure, which is also one of the, limitation of the direct shear test, जहाँ पर हम pore water pressure direct measure नहीं कर पाते, तो we use theoretical approach given by Skempton, in which he gave us two parameters. So what happened that in undrained triaxial test, applied stress used to show in the form of change in pore water pressure denoted by delta U. So Skempton gave two parameters, empirical parameters. One was A, the other one was B. These were used to express the pore pressure response under two distinct loading stages. जहाँ पे हमें पता है कि शेयर स्ट्रेस चैप्टर में ट्राइएक्सियल टेस्ट में दो स्टेजेस होते हैं. पहला होता है कन्फाइनिंग स्टेज, जिस कन्फाइनिंग स्टेज में हम बी पैरामीटर को डिफाइन करते हैं, और दूसरा होता है डेविएटर स्टेज, जिसमें हम पैरामीटर ई को डिफाइन करते हैं. लेट्स सी द फर्स्ट वन, द कन्फाइनिंग स्टेज, जिसमें कि सॉइल को लैटरली और एक्सियली सिग्मा 3 लोड से लोड किया जाता है, सेल प्रेशर जो वाटर देता है, वेयर डेल्टा यू सी यानी कि चेंज in pore water pressure in the confining stage is equals to B into delta sigma C, that is change in the cell pressure, or we can use delta U3 equals B delta sigma 3, since sigma C is nothing but sigma 3 minor principal stress. So the parameter B measures soil's pore water pore water response in the hydrostatic cell pressure sigma 3, or it represents the ratio of change in pore water pressure to the change in confining pressure. मतलब pore water pressure के change होने से confining pressure या फिर उल्टा कह सकते हैं in the change confining pressure के change होने से pore water pressure में कितना change आता है, that is measured by the parameter B. So this is represented by the formula delta UC by delta sigma C और delta UC by delta sigma 3. ड्राई कंडीशन में B की वैल्यू 0 होती है, सैचुरेटेड कंडीशन में B की वैल्यू 1 होती है, और पार्शियली सैचुरेटेड के केस में इट इज़ फ्रॉम 0 to 1. तो एक तरह से हम कह सकते हैं कि कहीं ना कहीं जो पैरामीटर B है, इट इज़ डिपेंडेंट अपॉन द डिग्री ऑफ सैचुरेशन. As you can see that P depends strictly on the degree of saturation. Then there is deviator stress stage, the second stage, or the shear stress loading, that is stage 2. In this, the parameter A is defined in terms of another parameter del A dash, whereas where A dash is written as A into B. Now the parameter A represents what? It represents the ratio of change in the pore pressure delta U sigma D to the change in deviator stress delta sigma D. We know that second stage में हर जगह से सिग्मा 3 लग रहा होता है, and then what we do is we apply sigma D, where sigma 1 is sigma D plus sigma 3 actually only. deviator stress सिर्फ actually लगाया जाता है, hence shear stress तक पहुंचने के लिए, और उसे increment किया जाता है till the shear stress or the soil fails in the shear. So A bar is written as delta U D by delta sigma D, and since we know that sigma 1 equals sigma D plus sigma 3, therefore sigma D can be written as sigma 1 minus sigma 3, therefore delta sigma D can be written as delta sigma 1 minus delta sigma 3. Now A depends on degree of saturation, the stress history of soil, the over consolidation ratio of the soil, the structural breakdown, or the volume change tendency of the soil, whether they are in contraction or they are dilative. So A is not constant for all soil, and it can vary from negative values to positive values. It is minus 0.5 for dense sand or OCC clay, and it is positive 3 for loose sand or NCC clay. So A can be less than 0 and A can be greater than 1. And negative pore pressure occurs in dilating soils such as dense sands and OCC. It makes the A negative for such soils. If on field sigma 3 and sigma D both are changing, then the total change in pore pressure delta U can be written in parts as delta UC confining stage and delta UD deviated stage. Or since we can write delta UC as B into delta sigma 3 and delta UD as A bar delta sigma 1 minus delta sigma 3, where A bar is nothing but A into B, B हम common करेंगे तो final expression बनता है, which is often asked in the exam, that delta U is change in pore pressure, or the total change in pore pressure is B bracket delta sigma 3 plus A into delta sigma 1 minus delta sigma 3. Hence in this question the correct answer was nothing but that the A can be less than 0 and greater than 1, whereas the B will always lies between 0 and 1, and hence Q and R are the correct answer. Let us see the 12th question. It says that consider the following statement in the context of capillary pressure in soil. First one is that pore water pressure is negative in capillary zone. Yes, it is right. Pore water pressure is always negative in the capillary zone. The second is that water is in tension in capillary zone. Yes, it is in tension or suction. That is why it is able to overcome the gravity force that is acting downwards. Then it says that capillary pressure is more in coarse grain soil. So no, that is not the case. On the contrary, capillary pressure is much more in the fine grain soil. Therefore, first and second statement is correct. Let us see it, the concept behind it. The concept is that if this is our ground level and beneath at a distance of HC we have the groundwater table. We know that the distribution of pore water pressure beneath the groundwater table is positive, and it is given by U equals to gamma W Z. Z is the height between the groundwater table and the place where we need to find the pore water pressure, and below it is positive and above it is negative, where the distance is HC as height of capillary rise. This is where the soil particles are in what? The soil particles rise above the water table due to the surface tension, because here is high pressure and low pressure, and there is molecular attraction or adhesion between the water and the soil grains, so they are able to generate a suction or tension. Hence the pore water pressure in the capillary fringe is negative, given by U equals minus gamma W HC. Now we know that height of capillary rise is given by C by E D10 Allen Hazens. So we can see that if dia of coarse grain soil is more, so the height of the capillary rise is also less, whereas for fine grain soils the D10 is less, hence the height of capillary rise is more. So yeah, if it is a coarse grain soil, we have very small capillary pressure and height also. It is nearly 0.03 meters. And for fine grain soil, we have higher capillary pressure, and the height of capillary rise is also from 1 meter, it can go up to 10 meters. Hence the first and second statement were right in the question. The first and second were right, but third was wrong, so the correct answer is 1 and 2 only. Let's move on to the 13th question. It says that the E log curve is represented by, so this graph is nothing but the graph of an OC clay, because we know the E log P graph, if this is E naught, initial void ratio, at first it goes something like this, and after the NC stage overcomes, then we get the OC clay graph. In the previous question we were on the E versus log stress curve. which was a representative of the OC clay. Let us now brush up the consolidation topic a bit, okay, and how this graph came here. So we know that in the chapter consolidation, we know that consolidation is nothing but expulsion of pore water or decrease in volume due to application of pressure, okay, whereas in compaction we have decrease in volume due to expulsion of air. Now consolidation is divided into primary consolidation and secondary consolidation, where primary consolidation is due to expulsion of pore water, whereas secondary consolidation is due to plastic readjustment of soil solids. Okay, now the rate of consolidation, it depends upon three factors. The first is permeability of the soil, the second is the length of the drainage path, drainage path shown by D, and the third one is the loading condition. Whereas in the secondary consolidation, it starts after primary consolidation. Second is that it occurs in plastic soils, like black cotton soil, which has high plasticity due to montmorillonite, and it happens similar to that of creep of metals. That is, for long period of time the constant load acts and volume change is recorded, but that change is due to plastic readjustment of soil solids, and it is generally 10 to 20% of total settlement, and it is more often seen in organic clays rather than inorganic ones. So to develop field conditions in lab, we use consolidometer. It is an instrument, consolidometer or oidometer, in which we have a setup something like this. We have gauge in it, we have a way to apply incremental pressure, and we have gauges to measure that, and we measure delta V, change in volume upon initial volume, by delta H by H naught, which is equals to delta E by 1 plus E naught. E naught is the initial void ratio, H naught is the initial height of the soil sample. It is performed on the saturated soil, and there are two types of oidometer. First is the fixed ring cell, where only the top plate moves and bottom remains fixed, and the other one is the floating ring cell, where both top and bottom plate moves. Now using these consolidometer, and when load is doubled in each stage, dial gauge reads readings at different time intervals, and we draw the settlement versus time graph. This is settlement, then this is time, and we observe that this is how the settlement versus time graph works for the sand, and this is how it goes for the clay. As you can see, settlement in clays is much more than that in sand, but the rate, because of the slope of sand, is much more. Therefore settlement in clay is greater than the sand because it has higher void ratio, but the rate of settlement is higher in the sand. Then what we do is we plot the void ratio versus effective stress plot, which is called as normal compression curve, and it goes like this. This is our void ratio and this is our effective stress on x-axis. Let us say E naught is the initial void ratio. It goes something like this, gives us an concave shape, and this shape is for a normally consolidated soil, NC soil. It reaches at a stage, say E naught, from initial higher void ratio to a smaller one because of the decrease in volume or expulsion of the pore water. Say initial pre-consolidation stress was sigma naught, and इस graph का the slope of this graph gives us our first coefficient, that is slope of E versus sigma curve, E naught minus E1 over sigma naught minus sigma 1, which is called nothing but or coefficient of compressibility. Coefficient of compressibility shown by AV, which is written as modulus because otherwise the value will be negative, as this, or we can write AV as delta E by delta sigma bar, which has units of meter square per kilonewton. And since AV is not constant for this curve, because you see it varies, because ये एक varying curve है, concave curve है, तो at different point we are getting different slopes. Therefore what we do is we then use a semi-log graph over this one, because there we get a straight line. Therefore we use void ratio versus log of effective stress graph. Here what we get is, for NC clay we get a straight line which has a constant slope. So this is a straight line, and this is for an NC soil where you reach E1 at a stress of log sigma 1 bar, and initially it was log sigma bar, and the slope for this curve is called coefficient of compression or compression index, which we draw as Cc equals delta E over log sigma 1 bar by sigma naught bar. If higher is our Cc, higher will be the settlements. Now let us see the empirical relation related to the Cc, that is compression index. Often many formulas are asked from this thing. So the empirical relations of Cc, coefficient of compression or compression index. First is for undisturbed clays. For undisturbed clays, Cc is given by 0.009 WL liquid limit minus 10, where WL is liquid limit in percentage. And for remolded clays, we write Cc as 0.007 WL minus 10, and sometimes we also write 0.007 WL minus 7 given by Skempton, but this one is generally preferred. And there is another one that for organic clays Cc is 0.0115 Wn, where Wn is the natural water content. Okay, now there is this term called pre-consolidation soil or over-consolidation soil. Pre-consolidation or over-consolidation, consolidation. So you see, if the present applied effective stress on any soil it is less than the past applied effective stress on that soil, तो फिर उसे कहा जाता है over consolidation. Over consolidation soil, where the present stress acting on a particular soil is less than the stress it has been subjected to in past. Let us say soil surface था जिस पे एक 3-4 स्टोरी बिल्डिंग था. मान लीजिए अगर हमने उसे डिमोलिश करके एक छोटा सा हट बनाया, तो दिस सॉइल कैन बी सेड एज अ सॉइल विच इज़ ओवर कंसोलिडेटेड, क्योंकि अभी जो इस पर स्ट्रेस लग रहा है वो कम है जो स्ट्रेस उस पर पहले लग रहा था. वो ऑलरेडी कंसोलिडिफाइड हो चुकी थी इस बड़े स्ट्रेस से. तो उस इसी कारण से ओवर कंसोलिडेटेड क्लेज जो हैं डेंस सैंड की तरह बिहेव करती हैं. they show higher bearing capacity, and they show less settlement also. And then we have what we have the pre-consolidated soil, where the present stress is greater than or equal to the past stress. That is, अब इस सॉइल पे हमने एक ऐसा स्ट्रेस लगाया जो इसकी हिस्ट्री में इससे पहले नहीं मिला. दैट इज से इससे पहले इसे सिर्फ 80 किलो पास्कल का स्ट्रेस था, बट अब हमने 120 किलो पास्कल दिया. तो नाउ इट विल बिहेव एज अ pre-consolidated or normally consolidated soil. Sorry, I was wrong. Pre-consolidation and over consolidation is one and the same thing. We will call it as normally consolidated soil. Yeah. Let us see now another point. Now we'll draw the a curve, and this curve will have 4 stages. This comes on in the consolidometer test only, where we have 4 stages of this curve. The first curve is normally consolidated curve, and this or it is also called as virgin compression curve. The second one is called rebound or swelling curve, and the third one is called over consolidation curve, and the fourth one is called normally consolidated curve. We'll see दोबारा का normally consolidated curve क्यों आया. So this is our first stage, this is second, and this is third, and this is fourth. So let's see what happens. Is this is our graph, on which we have effective stress, and this is our graph on which we have the void ratio. Let us say we had initial void ratio E0, and the soil was already subjected to its natural loading state sigma naught. Now as we increase the effective stress, this is how the soil starts varying in concave. We see as the load is coming, the voids are decreasing, there's going on settlement, there is expulsion of air, and then there is expulsion of the water. So void ratio decreases to a point. Let us say this point becomes, the void ratio decreases to the point E1, and at this point we reached, let us say, an effective stress of sigma 1 bar. Now when we lift this pressure, what the soil does is it starts to get back, because during this process of you know decrease in void ratio, what is happening, you know in between the soils, the soil is occupying or removing, due to the stress, the soil is removing the air between the voids, and this removal or the settlement that is happening within the soil solids, in the three phase or two phase diagram, there is elastic settlement, and then there is plastic settlement. And throughout this change from E0 to E1, elastic as well as plastic settlement has occurred. But as soon as you remove this sigma 1 bar, the plastic will remain there because you cannot get back, but it will try to regain the elastic settlement or elastic change in void ratio that had happened. So therefore it will try to regain that elastic settlement, and it will reach to the void ratio E2, which is relatively very much lesser than the E0, but it will nonetheless try to come back. So this becomes our second curve, whereas the first one was our first. The E0 to E1 was our first stage of the curve. Then what happens? We apply the load again, but this time the increment in stress is much more, in the sense that this time the change in void ratio does not happen that quickly, because the soil has already been to stress sigma 1 from sigma 0. When you try to go back to sigma 1 again, but this time you are not coming from E0, you are coming from E2. Now during the process of E0 to E1, you had already removed a lot of voids, the air between the voids, the water between the voids, and yes, due to the rebound or swelling phase, it did got back to some water got sucked again, because not all the particles were permanently deformed. So now the curve won't happen, now the curve won't proceed in the first stage manner, it will proceed in a convex manner. So this third stage is called as the over consolidation curve, because this soil has already been subjected to sigma 1 bar curve previously. So this becomes our third stage. Now when you will try to again load the soil beyond sigma 1 bar, the soil will again show the nature of curve similar to how it performs in a normally consolidated soil I had just showed before, in this way, which is a normal thing in NC soil. So here we get the NC curve again after sigma 1 bar, because again now the soil is getting loaded with a stress which it was not loaded before ever in its stress history. Okay, so now again when we try to shift some of these curves on semi-log graph, where we have log effective stresses on the x-axis and E0 over here, we start from E2, and this time due to log the curve is slightly convex, but it is not totally convex, it is a bit straighter, and it reaches E1 from E2. We are basically trying to recreate the third curve. This is our third curve, which was for the OC stage, and this was the curve, the fourth stage after we have, this was log sigma 0, and once we exceed log sigma 1 bar, we get the NC stage, again a straight line, but and this is the fourth stage, and this is a NC stage or NC soil. So in our given question, they had asked us which graph will show this sort of behavior. You see, this is not as straight as it looks. It is a bit, convex. It is not straight but a bit convex, not as convex as it was in this graph, but a bit convex. So hence our concept or answer to that question, where it was said that E log P कर्व में इस तरह की शेप का ग्राफ कौन सा होगा, तो इट वाज OC क्ले. Now we can also note these important points, that when we do the slope of E versus log effective stress curve, in OC stage, not NC stage, we get a coefficient which is called coefficient of not compression but this time recompression. So this is important. अगर OC स्टेज होगा तो वहाँ पर जो हमें स्लोप मिलता है E वर्सेस log सिग्मा बार का, तो that is called coefficient of recompression, written as delta sigma bar log sigma 1 sigma naught, and this CR is 1 by 5 to 1 by 10 of CC. And then we have the concept of over consolidation ratio, OCR, which is equals to maximum applied stress in past divided by maximum applied stress, effective stress in present. It can be greater than 1, it can be equals to 1 or less than 1. If OCR is greater than 1, that is stress in the past is more, then we are in OC stage or over consolidation. If the OCR is equals to 1, then we are in the NC stage, and if by some reason OCR is less than 1, we are in a under consolidation stage. Consolidation stage. This generally happens for an under construction soil, because धीरे धीरे वहाँ लोड बढ़ता रहता है, So yeah, let us now do one thing. What we'll be doing is that we will write down all the coefficients that are involved in the consolidation chapter. The first one is coefficient of compressibility, which we write as AV. Its formula is AV equals delta sigma by delta sigma bar, then we have delta E. Then we have coefficient of compression, which is denoted by CC. CC is written as nothing but delta E over log sigma 1 bar by sigma naught bar. Then we have third, coefficient of recompression. This is done for the OC clay, over consolidated clay. CR is written as delta E over log sigma 1 bar by sigma naught. And then we have fourth, that is volume compressibility, written by MV. This was CR. MV is written as AV over 1 plus E naught, AV from here. Then we have last, fifth is consolidation or coefficient of consolidation, written by CV. CV is written as K over MV dot gamma W, has units of meter per second, whereas all these four have unit of meter square per by kilonewton. Let's see the next question in the test. What was it? It was, consider the following statements. Capillary water in soil causes negative pore pressure. Yes, it causes. It reduces the effective pressure. No, it doesn't. On the contrary, in the zone of saturation, because we know it is sigma T minus mu, and sigma T in the capillary water, we often have negative pore water pressure. So the effective stress rather increases. Therefore, it does not reduce. Increases bearing capacity. Yes, it increases because it increases the effective stress. Hence, it increases the bearing capacity. Reduces, no. So the correct answer is 1 and 3. That is A, 14A. Let's see if we have the other questions. No. Let's move on to the next question. So here is another question, that a footing 2 by 2 into 1 meter exerts a uniform pressure of 150 kilonewton per meter square. Assuming load dispersion of this is to this, 2 vertical is to 1 horizontal, the average vertical stress below the footing. Now let us see the concept. The concept is that of 4-step method. यहाँ पर हमारा फुटिंग है जिसका विड्थ b है, दिस इज आवर df, दिस इज आवर ग्राउंड लेवल. तो कॉन्सेप्ट ये बोलता है कि जब एक फाउंडेशन के ऊपर यूनिफॉर्म लोड आ रहा होता है, यू नो, टूवर्ड्स द सरफेस ऑफ द सॉइल, तो स्ट्रेस जो सीधा ही एक कॉलम की शेप में नीचे नहीं जाता, बट ऑन द कॉन्ट्ररी वो एक डिस्ट्रीब्यूटेड एरिया या स्प्रेड आउट वे में एक वाइडर एरिया को कवर करता है ये लोड स्ट्रेस की फॉर्म में, जो एक ट्रेपेजॉइड बनाता है, समथिंग लाइक दिस, एंड दिस ट्रेपेजॉइड हैज़ a depth below the footing as z equals h naught by 2. Okay, and this slope is taken as 1 verticals to n, therefore this becomes nz, and this also becomes nz, and this whole becomes b plus 2nz. उसी तरह 3D में इनसाइड अंदर में इसका लेंथ हो जाता है 2nz along the length, and then we use the formula delta sigma, that is average stress, is equals to Q over L plus 2nz b plus 2nz. हमारे क्वेश्चन में हमें 2 वर्टिकल इज टू 1 हॉरिजॉन्टल दिया है, बट डेरिवेशन में वी हैव 1 वर्टिकल टू n हॉरिजॉन्टल, देयरफॉर 1 वर्टिकल के फॉर्म में हम लिख सकते हैं 1 वर्टिकल इक्वल्स टू 1/2 हॉरिजॉन्टल, देयरफॉर n इज 1/2, देयरफॉर और जो प्रेशर दिया है दैट इज 150. तो क्यू को हम लिखेंगे प्रेशर, क्योंकि ये लोड है, इनटू द एरिया ऑफ फुटिंग, दैट इज प्रेशर इज हाउ मच 150 into the area was 1 into 2 meter, to a footing 2 meter into 1 meter, this becomes 300 kilonewton. Now we will find out the area of the distributed trapezoid, that is L plus 2nz into P plus 2nz. Okay, length is, let us say the length is 2 meters, so 2 plus 2 into n is 1/2, and z is how much, z हम निकालेंगे अभी, and b, let us say b is 1 plus 2 into 1/2 into z, this becomes 2 plus z, and this becomes 1 plus z, and since z is taken as soil beneath the footing, इस क्वेश्चन में हमें कुछ दिया था about the depth beneath or not. Let us see. Yeah, if the depth is not given, we take depth as 1 meter. Therefore this will become 2 plus 1 and 1 plus 1, that is 3 into 2, that is 6 meter square. Therefore ये हमारा न्यू एरिया हो गया, this is our new area, and average stress is given as delta sigma as Q by L plus 2nz B plus 2nz, जो Q हमारा आया 300 और एरिया हमारा आया 6 मीटर्स, दैट इज़ 50 किलो न्यूटन पर मीटर स्क्वायर आंसर ए।